Hello and welcome to our next installment of the not public exam, but final exam review for Calculus 3208 on CVLI. And so this is our next topic is sort of continuing on with our theme of limits and continuity in this unit. And now we're going to talk about some limit laws, which are things that we can use to help us evaluate limits. And we're going to talk about how we evaluate some basic limits using those limit laws and a couple of other little tricks. But for now, we're just getting into the basics of computing units. So this is really our next big topic here, is about how do we actually calculate limits, algebraically that is. Okay, so let's get started. Calculating limits, so again, quick summary of all the things we're going to talk about. We want to look at limit laws, something called direct substitution property, and how do we calculate those basic limits. All right, now in this slide and the next one, I'm going to just quickly talk about a whole slew of different limit laws. Now these are all basically the theoretical underpinnings that we use that allow us to do all of the sort of computational business that we do with limits. Typically, most students don't spend any time memorizing these limit laws or actually going through a whole bunch of detail with them, but they're just to give you an idea that limits are pretty friendly in terms of how we can manipulate them algebraically. So let's look at what some of these things say. The first one is a sum or difference, and it says if I'm adding or subtracting two functions, then the limit of that sum is the sum of those limits. The same thing would work for a difference. The second one is a constant multiple. So the limit of a constant multiple times a function like this, well, what we can do is just pop that constant multiple out in front of the limit, and then we have, it's just the constant multiple times the limit of the function. The third one is a product rule for limits, and we usually read these as the product of a limit, or the limit of a product, is the product of the limits. And for a quotient, we can say that the limit of a quotient like these two is the quotient of the limit. So I can split that up, take the limit of the numerator, and just divide by the limit of the denominator, provided, of course, that the limit of the denominator is not 0, because that would not be permissible based on the laws of algebra. Now we're going to look at a few more limit laws. The next one is about a power of a function. So the limit of any function raised to a power is just the limit of that function, and then raise the result of that limit to a power. Okay, so that's pretty straightforward. And then the next one is a couple of special limits. The limit of a constant is just that constant, because it doesn't really matter what x does. If c is some constant number, then its limit is not going to change because its value doesn't change. And the limit as x approaches a of x, well, that seems pretty obvious. As the value of x gets close to a number, well, then x is getting close to that number. So that's basically all that says. So a couple of trivial little special limits there. Number 7 says the limit of a power function or of a root function. So this is really helpful for us, especially this first one right here when we go to evaluate limits of polynomials. What it says is that the limit as x approaches a of x raised to any power of n is just a raised to that power of n. So basically, we just fill the value of a in for x, and then that gives us a to the power of n. And that should seem to follow that the same thing would work for a root, because we do know that even if the exponent is not a whole number or not a natural number, then what we get are radical exponents for fractional exponents give us radical expressions. So the limit of a root is basically we just fill in the value of a, provided that it's not anything more complicated than just a root of x. And then for the root of an entire function, well, the rule there is the limit of a root of a function is the root of the limit of the function. So you can just flip the order, makes it easier to evaluate the limit of f of x, and then take the root of that one. Okay, so those are all those limit laws. No great amount of time spent practicing or looking at those or stating them, because 99% of the time, most of that stuff is fairly intuitive when we actually go to do some work. So the first rule for algebraic computation or calculation of limits is something called the direct substitution property. And it's fairly simple to run with. All we say for this is that for limits of relatively simple functions, the quickest and easiest way to evaluate the limit is to simply fill in the value of that x is approaching and then evaluate the function. For instance, let's look at these two examples here. The first one that we have says we want to take the limit as x is approaching 4 of x squared plus 3x minus 1. Well, this is a nice polynomial function, and it's continuous and all that good stuff. So if I want to evaluate the limit at any value of x, all I have to do is fill it in. So this would be 4 squared plus 3 by 4 plus 1. So that's 16 plus 12 plus 1. And that's going to be equal to 29. Okay, so that's really straightforward. Over here we have a radical function with a little polynomial inside for the second one. And in order to evaluate that, all we have to do is remember one of our limit laws says that the limit of a root of a function is just the root of the limit of the function. So it's the cube root of the limit as x approaches 33 of 3x minus 5. So then I know that for a polynomial like this one, and same thing over here now, I just have a linear, I can just fill in my 33. So that's going to give me the cube root of 3 times 33 is 99, and then I'm going to subtract 5, and that's going to give me the cube root of 94. And the cube root of 94 is not a perfect cube, so we'll leave that alone. We won't worry about simplifying or anything like that. We just want to evaluate it today. So that's our limit for that one. And this is the limit we had for the first. So there's a little note here that says if f is a polynomial or rational function, and a is in the domain of f, then very simply put, fill in the value of a, and you're in good shape. And the same thing works for radical functions, not just rationals and polynomials. Okay? So now let's jump on to our our first example that we're going to deal with, and we're asked to evaluate each of the given limits if possible. So for the first one, we know it's polynomial, so we just fill it in. So 3 times 2 cubed minus 7 times 2 plus 8. That will give us 3 times 8, which is 24, minus 14 plus 8. 24 minus 14 is 10. 10 and 8 are 18. So there you go. We've got our limit. So not much to that. And for the last one, we could apply the limit law here that says that the limit of a root or of a radical would be the root of the limit. But we already saw in our last slide that what happens when we do that, as long as the stuff we get under here isn't going to be a negative so that the radical is undefined, and it's not going to make a big difference. We can just use direct substitution again and fill it in and see what happens. If it works, we're in good business, or we're in good shape, sorry. And if it doesn't work, well, that's it. We can't evaluate. So we're going to take the square root of 15 times negative 2 squared plus 10 by negative 2 minus 4. So what is that going to give us? It's the square root of 15 times 4, which is 60, minus 20, minus 4, and 60 minus 24 is 36. So the limit for that function is, the square root of 36, isn't it? So we've got the square root of 36, which equals 6. So our limit there is just 6. Okay, so 2 very straightforward limit questions. Fill in the value of x and hope for the best. Our next example says we have to evaluate the limit for each of these if possible. Now, the first one we have is the limit of an exponential function subtract a linear function. 13x is what we're taking away from this. Well, for that, we have sort of the difference of 2 functions that are very different types of functions. But we have a limit law, as we saw, that says we can simply split this up. So it's the limit as x approaches 2 of 5 to the power of x minus the limit as x approaches 2 of 13x. So all I have to do now is fill in my values. So as x approaches 2 of 5 to the power of x, we get 5 squared. And as x approaches 2 of 13x, we get 13 times 2. So our limit here is going to be 25 minus 26. So we have a limit of negative 1. Okay, so pretty straightforward there. For the next one, we have a rational function, and it says, what's the limit as x approaches 5 of this expression? Now, we have to be a little bit careful with this one. This is not as straightforward as the others. For right now, the only real technique we have for evaluating limits algebraically is just to fill in the value and see what happens. And if we try that here, we get 5 squared plus 3 by 5 minus 10 all over 5 minus 5. Aha! So in the numerator, we've got 25 plus 15, which is 40, minus 10 is 30. But in the denominator, we have 0. Uh-oh, that's undefined. What does that mean? Well, sometimes when we get something like this, it means the limit doesn't exist. In this case, we don't really know for sure whether the limit exists or not, because we don't know how to evaluate a limit like that. But not yet anyway. And for now, all we can say about this is that this is an indeterminate form. And for an indeterminate form, the limit may exist, but we can't do it yet. So we're not sure yet about what's going to happen with this one. It turns out actually that the limit in this case doesn't exist, but we have to see why, and we'll get to that in a future session here. Okay, so now let's take a look at a couple of exam type questions. So the first one, would be a constructed response question. It just says evaluate the limit as x approaches 3 of, we have a linear function, and then we have subtract an absolute value function. So let's just try to fill it in and see what happens. And basically the cardinal rule with that direct substitution property is try it. And if it works, great, you're done. If it doesn't work, you may have to try something else. So let's try direct substitution here. And if I try that, what I end up with is 9 plus 5 minus the absolute value of 0, which is still 0. So I get a limit of 14, and everybody's happy. So direct substitution worked. We don't have to investigate any further. The next question says, which is true of this limit? Okay, so we've got some multiple choice business to consider here. So let's look at what's happening with these different things they're trying to tell us. Well, there's a whole lot of things about whether it exists, whether it's an indeterminate form, whether the limit cannot be evaluated with limit laws, and the last one actually says that it can be evaluated because of a not zero. Whoa, that's a lot of stuff. Why don't we just go back to what we had and see if we evaluate the limit what happens, and that might make answering this question a bit easier. So if we try to evaluate this using direct substitution, we just get 2 squared plus 3 by 2 plus 1 divided by 2 plus 1. And that's going to be 4 plus 6 plus 1 all over 3. 4 and 6 and 1 are 11. So we have 11 thirds. And that seems okay to me. So to say the limit does not exist, I'm not happy with that one. To say it's an indeterminate form, nope. The only thing we saw that gave us an indeterminate form, and like we saw in our note earlier, is we can take the limit of a rational function as long as this stuff doesn't end up being 0. And since it doesn't here, we have no worries. Part C says the limit cannot be evaluated with limit laws. Well, technically, because this is a rational function, we're taking the limit of a numerator divided by the limit of a denominator by filling these things in here. Then we're taking the limit of a whole bunch of sums. We never really think about the limit laws, but every time we evaluate a limit by direct substitution, we are really using them. So the limit cannot be evaluated with limit laws. I don't buy it. I think it can because we just did. So it's got to be the last one. Let's see if we can understand it. The last one here says the limit can be determined. Okay, so that's a good thing. Since the denominator is not 0 at the given value of x. And that's absolutely correct. Since the denominator is not 0, the direct substitution property will work. Everybody's happy. We're off to the races, and we're done. Okay? So next up is the your turn question. So there's a couple of limits for you to try to evaluate there by direct substitution. And be careful. If it doesn't work, it doesn't necessarily mean it doesn't exist. It just means that at this point, we don't really know how to evaluate it yet. So good luck with those. I'm going to flip and show you the solution now. So pause the recording if you're working those out. So there's the solution to the your turn question that we have. And from that solution, you should be able to work out just about anything you need. And otherwise, I'm just going to highlight the key points from this section that we talked about. First of all, there are a number of limit laws, and most of them are pretty straightforward, so no big deal there. They make evaluating limits algebraically more convenient, and that's all there is to it. In everyday practice, we usually don't think about those limit laws, as they are mostly intuitive. As a basic rule, we can use direct substitution property to evaluate a limit whenever it works. So that's the big key thing there. We can use it whenever it works. If it doesn't work, we might have to try something else, or we might be out of luck altogether. But if it works, go with it. And the second last one here says, if a limit cannot be evaluated by direct substitution, it's possible that it does not exist. And the last one says, it is also possible that it might exist. So we have to employ some further technique to evaluate it. Okay, hope this was helpful. Getting started into some limit business here. So happy studying and good luck.